So, an example here, weights of diamonds are measured in carats. 1 carat is 100 points. So 0.99 carats is 99 points, etc. The difference between the size of a 0.99 carat diamond and a 1 carat diamond is undetectable to the naked human eye. But we want to know if the price of a 1 carat diamond tends to be higher than the price of a 0.99 carat diamond. So we're going to test to see if there's a difference between the average prices of 0.99 and 1 carat diamonds. We want to be able to compare equivalent units, so we're going to divide the prices of the 0.99 carat diamonds by 99 and the 1 carat diamonds by 100. So we get the average point prices. So this is from, this is a data set from an R package. It is a random sample of the diamonds in the data set. And we can see here, it looks like the means of the two distributions are pretty similar, but the variability or the shape of the two distributions is very different, right? The 0.99 carat diamond distribution is skewed to the left, whereas the 1 carat diamond distribution is skewed to the right. So identify our parameter and our point estimate. Our parameter is the average difference between the point prices of all 0.99 carat and 1 carat diamonds. Point estimate is going to be the average difference between the point prices of the sampled 0.99 carat and 1 carat diamonds. Which of the following does not need to be satisfied in order to conduct this hypothesis test using the theoretical methods? Point prices of 1 0.99 carat diamond should be independent of each other, and the point price of the 1 carat diamond should be independent as well. That is something that we need to check or assume. Point prices between the two groups should be independent. That's something we need to assume. Distribution of point prices of 0.99 and 1 carat diamonds should not be extremely skewed. And they are skewed, but they're not extremely skewed. We do not need to check that both sample sizes should be at least 30. So we would want to check the sampling distributions for both. So if the sampling distributions are approximately normal, or if our sample sizes are at least 30. So when you're adding or subtracting two distributions, you add or subtract the means. So the sampling distribution for the difference of two means is going to be the difference of the means of the populations. For the standard deviation, we take the variances, divide them by n, add them together, and then take the square root there. So what's the difference of the sample means? So 44.5. 44.5 minus 53.43 is going to be negative 8.93. The standard deviation of the sampling distribution is going to be the square root of 13.32 squared over 23 plus 12.22 squared over 30. which ends up being 3.56. Suppose the actual prices of a 0.99 carat diamond are on average the same as the actual prices of a 1 carat diamond. So suppose the true mean of this distribution is 0. What percent of samples would have a difference of at least the difference we see? So we've checked our conditions. We can model this using the normal distribution. We're assuming that the mean is 0, and we want to know what is the probability that we get a difference that is at least 0.893. So we can do this using the normal CDF with a lower bound of -1E99, an upper bound of -8.93, a mean of 0, and a standard deviation of 3.56. However, it does say a difference of at least the difference we see. It doesn't say that the 1 carat diamonds are bigger by this much. So we also want to check the other tail, a difference of 8.93 in the other direction. Now, fortunately, these two tails are the same because the normal distribution is symmetric, so we can just find one tail and then multiply that by 2. And if we do this, on the calculator, we're going to get a probability of 0.012. So if the price per carat of the 0.99, or price per point of the 0.99 carat diamonds and the 1 carat diamonds are the same, there is a 1.2% chance that we would get a difference this extreme. That does not seem very likely. So more likely, the 1 carat diamonds are actually cost more per point. And that's it. That's the difference of two sample means.